Okay, good morning, students. Today we are going to discuss the continuation of the same topic, chemical equilibrium. Okay, chemical equilibrium. Okay. So in that chemical equilibrium lesson, we are going to see the subtopic Van Hoff equation, Van Hoff equation. Okay. First of all, what is this Van Hoff equation? And what is the relation behind this? Okay, if you analyze, this comes under equilibrium lesson, this Van Hoff equation, and it gives a measure, that is measure of quantitative temperature dependence of equilibrium constant. That is, it is a measure of quantitative temperature dependence of temperature dependence of equilibrium constant. Okay, so from that it is very clear. Okay, we are going to take that as it gives a relation between temperature and also equilibrium constant. Okay, we know already what is temperature. Okay, so temperature means what happened, whatever may be the reaction, how much temperature is involved. That is depends upon the measuring of a temperature. And one more concept we want to know about equilibrium constant. So in that lesson, in a chemical equilibrium, we know what is equilibrium constant. That is, how you know that the equilibrium constant. Okay, so being it is a constant, we are going to explain in terms at the condition of a equilibrium. So we know that what is equilibrium? It is a stage, okay, where we are going to see whether the reaction is completed with the product or the reaction is back to the reactant. Okay, we know that there are two conditions. One, the reactant molecule should react in such a way that we are going to get the product. So during the formation of the product, we know that all the reactant molecule should cross over that energy barrier. We know that it is called the energy barrier, that is called the activation energy. Suppose if I am taking one reactant, okay, so the chemical equilibrium equation, okay, so the reactant I am going to consider the two. One is A reactant and another one is a B reactant, like that. If I take A as A moles and B is B moles, likewise, okay. And whenever this should be considered as a reactant. Okay, what is this? This should be considered as a reactant. Okay, now this reactant reacts in such a way that, okay, that is existing in an equilibrium, okay, and it gives a product. Okay, the product we are going to take C and D, or the two products, whatever may be. So just I am giving in general, C and D are the two products. Okay, and C I am going to take C moles of a C as one product and P moles of a D as another product, and this is considering as a product. Okay, why I am indicating the equilibrium that is symbol here. So it is used to indicate whether the reaction, first of all, A and B, there are two reactants that reacts in such a way that you may get a product. Okay, and same manner, okay, again the C and D are the two products, okay, acting as a reactant, and the reaction should be what? Reversed, and you may get A and B are the two products. Okay, so this shows that the equilibrium existing between the reactant and the product. So it should be very clear. So the reactant should be converted into product, or again the formed product there can be converted into reactant. Okay, so this is clear. Okay. From that I am going to explain what is called the equilibrium constant. Okay, so what is equilibrium constant? So equilibrium constant we can represent in terms of a letter K. This is only called a equilibrium constant. This is what? Equilibrium constant. Okay, now how can I represent this equilibrium constant K? So it is a measure of the ratio of the product of the concentration of the products. That is, it is a ratio of, okay, ratio of product means it's a multiple product of product concentration with product of multiple product means product of reactant concentration. Okay, generally reactant concentration. It is understood. The product means what? It is a multiple. You may consider one product or two product or three product. It depends upon the what reaction. So what is equilibrium constant? It is a ratio of a product of the product concentration with the product of the reactant concentration. So it is nothing but ratio of the concentration of the product to the concentration of the reactant. Okay, so is it clear? Okay. Now, how can you write the equilibrium constant for a given equilibrium reaction? Okay, so just I have considered A and B are the reactant, C and D are the product. So I can write here one product C. So concentration term I should indicate like this C. Okay, and number of moles, how much number of moles? Yeah, C. Okay, so C as a number of moles, power. And next, if I take the another reactor, that is another product D. It is a product of a concentration of the product only. So one concentration C, another concentration D, number of moles D, and it is a ratio that should be divided by concentration of A. It is nothing but A, and number of moles A, and concentration of a B as another reactant, and number of moles is a B. This is called equilibrium constant. How to express an equilibrium constant for a given reaction? Whatever will be the equilibrium process, you should keep it in your mind. So how will you write the equilibrium constant? Equilibrium constant, it is nothing but you should take the ratio of the product concentration and the ratio what to the reactant concentration and the powers, that is the number of moles that should be indicated in the powers of the concentration. That is only called the equilibrium constant. Okay, now in this Van equation, just we are going to derive a relationship between temperature dependence of a equilibrium constant. How that equilibrium constant depends on the temperature That I am going to explain in that Van Hoff equation. So shall we go with the Van Hoff equation? Okay, so that is the explanation. So first of all, what is if you want to explain Van Hoff equation? Okay, we should be very clear about. Okay, so what is called a standard free energy? Okay, so the relation between standard free energy, that is the relation between standard free energy change, okay, the relation between standard free energy change and equilibrium constant, okay. So what is standard free energy change? We know that it is an energy involved in the reaction, and equilibrium constant, we know it is K. How to represent K? We know already. Okay. So the relation between standard free energy change and the equilibrium constant given by the expression. Now I am going to give one expression, that is how to relate this equilibrium constant with the free energy. Okay, so that relationship I am going to explain, that is del G naught, that will be equal to minus RT ln K. Okay, RT ln K. If you take, this is a mathematical expression that gives a relation between free energy with the equilibrium constant. Okay, free energy with the equilibrium constant. We know del G naught. This is standard free energy change. Standard free energy change. This is what a del G naught. Okay, G is what a free energy. Now, just standard means we should indicate this naught. Okay, this represents standard condition. This represents what a standard condition. Okay, standard free energy change. Del represents a change. What del represents? Change. Okay. This is what standard free energy change. Okay, and what is R? Okay, R, we know that it is a gas constant. It is gas constant. Okay, and what is here T? Here T is temperature. That is how much temperature involved in that reaction. Okay, and same way, if you take K, this K only known as equilibrium constant. Okay, this is only called what a equilibrium constant. Okay, so if you take del G naught, that will be equal to minus RT ln K. So where del G naught is nothing but what? Standard free energy change. Where R is nothing but gas constant, and T is called the temperature, and K is called the equilibrium constant. Okay, so this mathematical expression gives a relation between free energy and the equilibrium constant. Okay, next, so this equation del G naught minus 40 ln K, this mathematical expression will consider as a first equation. Okay, and next I'm going to give one more equation for a del G. Okay, from thermodynamics. Okay, if you take from thermodynamics, we know that how this free energy is related with the enthalpy and the entropy. Now I am going to give a relationship, that is what is this del G naught. Okay, so from the thermodynamics, we know that del G naught that will be equal to del H naught minus T del S naught. This is a mathematical expression that is obtained from the thermodynamics. Okay, so now you compare the first equation del G naught equal to minus RT log K. The second equation also just I am explaining del G naught, it is nothing but del H naught minus T del S naught. Okay, now here, what is this del G naught? We know already this del G naught is nothing but, okay, what is del G naught? This del G naught is standard free energy change. Standard free energy change. Standard free energy change. Okay. Now, next, what is this del H naught? So, this is a standard enthalpy change. Standard enthalpy change. Change in enthalpy at a standard condition. Enthalpy means what? Heat involved in the system. Heat content of a system. Del H naught. Okay. And what is T? This temperature involved in the system. T is a measure of temperature. And del S naught, it is nothing but standard entropy change. What is this? Entropy change. We know that what is entropy? Entropy is a measure of, okay, so it is a measure of disorderness. Measure of what? Disorderness in the system. Measure of disorderness in the system. So, from a thermodynamics, we come to know that del G naught equal to del H naught minus T del S naught, where del G naught is a standard free energy change and del H naught is what? Standard enthalpy change, and T is the temperature involved in the system, and del S naught is what? Standard entropy change. Okay. And what is entropy? We know already. It is a measure of what? Disorderness or randomness in a molecule. Okay. Now we know that two equations. Okay. So the two equations which relates what? Del G only. Okay. Now I am going to substitute. Okay. I am going to substitute. Substitute equation 1 in equation 2. Okay. So what is the first equation? Del G naught equal to minus RT ln K. Okay. What is second equation? Del G naught equal to del H naught minus T del S naught. Okay. So these two equations I am going to substitute. Minus RT ln K is what? Del G naught. That del G naught I am going to substitute in the second equation. So I'll get minus RT ln K. That is what? Del G naught. What is del G naught? Standard free energy change. That is a measure of what? That relates enthalpy and entropy. That is in another equation. Del H naught minus T del S naught. Okay. So this is a substitution. Substitute equation 1 in equation 2. We know that what is equation 1? 1 is what? Del G naught equal to minus RT ln K. Okay. This del G naught minus RT ln K. I am going to substitute in the second equation as del G. Okay. Here del G naught. So this I am going to substitute. Okay. So from substituting del G naught minus RT ln K, I am going to get a new equation minus RT ln K. That will be equal to del H minus P del S naught. Okay. So where the equilibrium constant related with the free energy. Okay. Now, if you take that, just I am shifting this minus sign with the another sign. Okay. So where I get T ln K R divided by minus sign. Okay. Minus del H naught plus P del S naught. Okay, so just we are dividing this equation by a common factor minus. So we will get a RT ln K, that will be equal to minus del H naught plus P del S naught. Okay, so now we keep the ln K in a one side. Okay, so ln K one side. Keep on, you take RT in the another side, you will get del H naught divide by RT plus P del S naught divide by RT. Okay, we know that T as common, so you cancel this T here. Okay, and next we come to get ln K is nothing but minus del H naught divided by RT plus del S naught divided by R. So this is the equation we are going to get. Okay, after substitution of a first equation in the next. Okay, so this equation we will consider as a third equation. Okay, after substitution. Okay, and next step I am going to differentiate this third equation with respect to temperature. Okay, I am going to differentiate. Okay, differentiate with respect to temperature. With respect to temperature. Okay. Now, if you differentiate this with respect to temperature, I'm going to differentiate that equation. So this ln K on differentiation, this becomes D ln K with the dt, because I'm going to differentiate with what? Temperature. So D ln K with the dt. Okay, and next I'm going to differentiate minus del H naught by RT. Okay, this is one factor. And if you take del S naught divided by R, here the temperature is not involved. So the differentiation that will be equal to 0 here. Okay. So first you take this del H minus del H naught divided by RT. Okay. Now I am going to differentiate this del H. Okay. I am going to differentiate this minus del H naught divided by RT. Okay. So first I'm going to differentiate only this term. Okay. So on differentiation, how can you differentiate? We know that here this del H naught under R is a constant. Okay, it is not possible to differentiate. You take it as outside. So minus del H naught divided by R, you take it outside. Okay, and what is remaining? 1 by T. What is remaining? 1 by T. Okay, and if you take this minus del H naught with R, okay, this 1 by T, I can write T the power minus 1. Okay, write what is T the power minus 1. Okay, next I'm going to simplify this T the power minus 1. Okay, so now you take T the power minus 1, I can simplify by using the relation. By using the formula x, okay, n x n power minus 1. Okay, so if you take t the power minus 1, just this t the power minus 1, if I apply the formula on differentiation, this is the formula n x the power n minus 1, t the power minus 1, I can write minus 1 t the power minus 1 minus 1. Okay, on simplifying this you may get minus 1 t the power minus 2. Okay, so it is nothing but minus of 1 by t square. Is it clear? Okay, so on just I am keeping del H naught divided by r as a constant. Now that constant I am keeping is one side. Okay, remaining factor 1 by t, that I am going to consider as a t the power minus 1. On differentiation t the power minus 1 by using the formula n into x the power n minus 1. If I supply that formula into t the power minus 1, so I get minus 1 t minus 1 into minus 1, where I get minus 1 t the power minus 2. Okay, that whole thing I can write minus 1 by t square. Okay, now this minus 1 by t square, this minus 1 by t square only differentiating formula. Okay, so if I substitute like here, that is already minus del H naught by r. Okay, into this t the power minus 1 on differentiation, you will get what? Minus minus 1 by t square. Minus 1 by what? T square. Okay, so on the whole you may write that will be minus into minus will get cancelled. So del H naught divided by r, this t square as it is. Okay, this is the one term differentiation. Okay, if you differentiate del H naught, del minus del H naught divided by RT, okay, you are ended with del H naught divided by RT square. So you should be clear with that step. Okay, so if you clear with that step, just you take that what is del H naught divided by RT, I am going to substitute in that equation. Okay, so this is del H naught divided by RT square. Okay, RT square plus we know that already. Okay, so this del H naught. Okay, just I am substituting del H naught divided by RT as well. Del H naught divided by RT square differentiation. Okay, but del H naught divided by R is not having a temperature term, so that should be taken as 0. That should be taken as what? 0. Okay, so now this equation again we are going to modify. Okay, now you take that equation. So you take keeping that d ln k in one side. Okay, now you take dt into the another side. So del H naught divided by RT square into dt. Okay, so now the differentiation, just we are going to get it inside on the right side. That is dt, RT square into dt. Okay, so now we know that this equation differentiating with respect to temperature. Okay, now this is a differentiating equation. Okay, next the same equation now I am going to integrate. Okay, so on integrating the same equation, okay, the equation, on integrating the equation with limits. If I use for k the limits K2 and K1, okay, and temperature I can take the limits T2 and T1. Okay, just I am going to integrate the differentiating equation with respect to what? The limits between the two different equilibrium constant and two different temperature constant. You take that equation T ln T. Okay, now I am going to integrate. Okay, so integration of a d ln k, because it is in the left side. Okay, so integration of a d ln k. Now I am applying a limits k1 and k2. Okay, you know upper limits and the lower limits, and same way the right side if I am taking integration. Okay, so the integration you are not applying to the constant. You take the constant out. Del H naught divided by R. This is a constant. You should take it outside. Okay. On integration, T1 and T2. Between the limits T1 and T2. Now the term remaining is what? T square. 1 by T square into dt. Into what? dt. Okay. Now listen. So this is integrating equation. Now I am going to integrate. Okay. So by using of integration symbol between that limit, just I am writing. Next step I am going to integrate. You take a left side. Okay. So integration of a d ln k. So integration of a d ln k, what it is? Ln k. Okay. D ln k, what it is? Ln k. Okay. So this ln k. Just we are going to apply the limits k2 and k1. This is left side integration. Okay. Next, we go with the right side integration. Okay. And we know that it is a constant. You write a constant as this. Del H naught divided by R. Okay. Now I am integrating 1 by t square into dt. Okay. We know that 1 by t square into dt. Okay. Now I am going to apply one formula, that is, okay, we know that already. Integral of x n into dx, whatever may be. Just I am giving in the x form. Okay. This as a formula, x n plus 1 divided by n plus 1. This is a formula. Okay. So integration of x power n dx, that will be equal to x n plus 1 divided by n plus 1. Okay. Now you take a integration of a 1 by, that is integration of a 1 by t square. I can write what? T the power minus 2. Okay. Into dt. So instead of x, we are taking what? T. Okay. So on same formula, same methodology, we are going to apply. So the t, okay, power n is what here? Minus 2. So minus 2 plus 1 divided by minus 2 plus 1 here also. Okay. So here you consider x as what? T and n is minus 2. So the substituting this into the formula, we will get t the power minus 2 plus 1 divided by minus 2 plus 1. Okay. Now we have to simplify this step. Okay. Now you take this. On simplification, we know that t power minus 2 plus 1 minus 1. Minus 2 plus 1 minus 1. So we'll write on the whole this minus. Okay. T minus 1, we will take 1 by t the power 1. So generally you may write minus 1 by t. Okay. So t power minus 1 is what? When it comes down, you get t the power 1. So this minus. So I'll write minus 1 by t. So on integration of t power minus 2 into dt will give what? Minus minus 1 by t. Okay, this is integrating value. Okay, now I'm going to substitute this integrating values into the equation. Already just I have integrated left side. I took a constant in outside. Okay, now the integration of 1 by t square into dt. This integration. Okay, integration of this. Okay, 1 by t square into dt. I'm getting what? Minus, okay, minus 1 by t. Okay, minus 1 by t within the limits. Okay, we should take the limits. So t1 and t2. Okay, so this is the integration equation. Okay, next step we are going to simplify this integration equation. Okay, just ln k. So ln k, we have to apply the upper limit first and the lower limits. So applying upper limit will get ln k2 minus ln k1. Okay, so the K, we should apply first the upper limit minus lower limit. So we'll get ln K2 minus ln K1. Okay, next it is a constant. Del H naught divided by R is a constant. Okay, so I'll write the constant as it is. Del H naught divided by R is a constant. You take a constant as it is. Okay. Next, minus 1 by T. I'm going to apply the upper limit first and lower limit. So upper limit minus 1 by, instead of T, apply T to minus. This is a minus sign in the formula. Minus of 1 by T1. So lower limits. Okay. So on applying the upper limits minus T2, okay, upper limit is T2 and lower limit. So minus 1 by T2 minus, this is a formula, and minus it is in the expression. So minus T1, okay, on the whole. This ln K2 minus ln K1, I write ln K2 divided by K1, ln A minus ln B formula. Okay, so ln K2 divided by K1. Okay, on taking this del H naught divided by R as a constant, you keep it in the other side. Okay, on simplification, this I write 1 by T2 minus 1 by T2. This minus and minus. Okay, change it as plus 1 by T1. Okay, 1 by T1. Okay, next step. Again, you are going to take a LCM for a minus 1 by T2 plus 1 by T1. Okay. So left side, no change. Ln of K2 divided by K1. So that will be equal to del H naught divided by R as a constant. And if you take a LCM, okay, we'll get here this T1 and T2 as a common factor, and or taking this T2 minus T1, this becomes, okay, T2 minus T1 divided by T1 and T2. Okay, now this is an expression in terms of what? Ln values. Okay, and next step I'm going to change this ln value into log. So we know that how will we convert this ln into log? Okay, so on multiplying with the 2.303, that is 2.303, we will convert this ln value into what? Log. So log of K2 with K1 will be equal to del H naught divided by R, and same temperature T2 minus T1 divided by T1 into T2. This is the expression. Okay, and the same expression, if you take the same equation, if you are divided with the 2.303 again. Okay, so if you are divided this the equation with the 2.303, are taking the 2.303 value on the another side. Both are same. So if I am divide log K2 divided by K1 is nothing but del H naught. Just we are dividing with the 2.303 value. So 2.303 into R, and the same temperature value T2 minus T1 divide with T1 and T2. Okay, this is a temperature difference. Okay, now this is called the, okay, this relationship only Van 't Hoff equation, and this Van 't Hoff equation just we are going to apply the problems. Okay, and what is this? Already I told you, this is a measure of water or a relationship between the equilibrium constant K with the temperature. Okay, so here the equilibrium constant, we took two equilibrium constants because it is a difference K2 and K1. Log K2 divided by K1, and the two different temperature we are considering T1 and T2. So this Van 't Hoff equation that is a relationship between the equilibrium constant with the temperature. So that only the Van 't Hoff equation, we name it as the temperature dependence equilibrium constant. Okay, what is that? Temperature dependence equilibrium constant. So the derivation, just we are derived that what is the relationship between the equilibrium constant with the temperature dependence. Okay, so if you go with the Van der equation. Okay, now we know that the Van der equation, it is a measure of, just started with, it is a measure of quantitative temperature dependence of a equilibrium constant. Okay, this first line, for the first line explanation, at the last I gave a formula. Okay, now what is the equilibrium constant? Okay, so it is equilibrium constant is nothing but what? So it is a equilibrium constant, it is nothing but it is a ratio of the product concentration, that is ratio of the product concentration with the product of a reactant concentration. Okay, this is called a equilibrium constant. Okay, now just I took one equilibrium reaction where I consider two reactants A and B and two products C and D. Okay, just I am indicating that is a equilibrium reaction. So equilibrium reaction means it is understood where you get a product conversion. Again, the product that will be converted into reactant. So equilibrium constant, okay, just I am indicating. Okay, here. Okay, it is a product concentration with the reactant concentration. Okay, next, just I am going with the derivation part. Okay, first we have considered the relation between standard free energy change and equilibrium constant given by the expression. What expression we do? Del G naught, that will be equal to minus RT ln K. So what is del G here? Standard free energy. Actually, G is free energy, not standard. Changes involved in del. So del G naught is what? Standard free energy change. Okay. Now what is R? R is a gas constant. What is T? T is a temperature and K is a what? Equilibrium constant. Okay. Now I took a first equation that gives a relationship with the free energy with the equilibrium constant. Okay, that may be a one-word question. Okay. And next I took from thermodynamics. Okay, I took one mathematical expression from the thermodynamics that gives a relationship between del G naught. Okay, del G naught. What is this del G naught? Standard free energy change. Okay, that will be relation with the del H naught. What is del H naught? Standard enthalpy change. Okay, and with the del S naught, T del S naught. T is a temperature and del S naught is nothing but standard entropy change. Okay. Now what is standard entropy? So entropy is what? It is a measure of randomness or a disorderness in a molecule in the system. Okay. Now just we are substituting the equation 1 in equation 2. Okay. The first equation what we took? Minus RT ln K. What is del G naught is equal to minus RT ln K. That RT ln K, just I am substituting in the second equation. Okay. Next, just on the whole equation, we are dividing with the minus sign. So RT ln K will be equal to minus del H naught plus T del S naught. Okay. And next step, we are taking RT in the another side. So we will take ln K. Okay, ln K, that will be equal to minus del H naught divided by whole system divided by RT. 2 side. Okay. And next we took ln K is nothing but minus del H naught divided by RT plus, okay, here TT has cancelled and you will get del S naught divided by R. Okay. And the same, that equation just we are differentiate with respect to temperature. Okay. And if you take minus del H naught divided by RT, that term is consisting of a temperature, so we can differentiate that term but del S naught divided by R. Okay, is not having a temperature term, so there is no differentiation. So that value should be considered as a 0. Okay, so if you take the del H naught divided by RT, okay, if you take this del H naught divided by RT, the whole thing just on differentiation. Okay, so if you take a differentiation, you take a constant, that is del H naught here. Okay, del H naught divided by R, you take it outside, and what is remaining? This 1 by T. Okay, so that 1 by T, I took as it is 1 by T, and I have taken this 1 by T as what? T the power minus 1. By using the formula n x the power n minus 1, just I am differentiating this. Okay, nx n minus 1. Okay, by using this formula nx into n minus 1, we are giving that minus 1 by t square, that will be converted into minus 1 t the power minus 1 minus 1, and we are getting what? Minus 1 by t square. Okay, now this term I am going to substitute in the minus del H naught R. Okay, that minus, okay, substituting that minus del H naught divided by R into minus 1 by t square. We are getting what? Del H divided by R. Okay, RT square. Okay, the same equation, just again what I am integrating. So the on integration, for the same equation, okay, we are getting the relationship log K2 divided by K1, that will be equal to del H naught divided by R. Okay, again, so to convert log into log, just we are multiplying with the 2.303, and the same 2.303, just I am dividing with the whole equation. The last final, what is the relation between the equilibrium constant and temperature dependence we got. Okay, this is a Van Hoff equation. And students, this is an important derivation. Can become exam point of view. This is a 5-mark question. And where we will get what is called equilibrium constant as a 1-word question, and sometimes they may ask how to write equilibrium constant for a given reaction. That may be a question also. Okay. Students, now you may ask your doubt. Can you hear me first?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Doubt in the equation you are telling us. Shall I consider that for yes? What is it? The answer. Do you understand what is Van Hoff equation?
Yes, ma'am.
What is the relation to Van Hoff equation?
Log
Yes.
K2 by K1.
Log K2 by K1 equal to del H naught by 2 naught
Del H naught by
or
By
2.3 minus 3 by
303
K1
R.
K0
Difference is
K2
T2 minus T1 divided by T1.
T1 divided by
T2 minus
T2.
T1 by T1 into T2.
Okay, any doubt in the Van Hoff equation?
No, ma'am.
No, ma'am.
doubt, ma'am.
No, ma'am.
Any doubt? You may ask one. Okay.
Yes, ma'am.
Okay.
Yes, ma'am.
Don't hear your voice.